Welcome. In this presentation we're going to talk about the simple linear regression model and how we do things in R. It's one of the most frequently used statistical techniques, and it's the basis of what we do in this course a lot. Let's start with a simple example with an X variable that is called duration and a Y response variable that's called interval. And these data are from the Old Faithful geyser in Yellowstone National Park. Duration means how long the previous eruption was in seconds, and the response variable is interval, which measures how long do you have to wait in minutes from the end of the last eruption till the beginning of the next one. And so this is really an issue about when you visit the park and the Old Faithful geyser has erupted previously, how long do you have to wait for the next eruption? And what you can see in this display is that there is an increasing pattern showing that when the last eruption was longer, like 200 seconds or 250 seconds, you tend to have to wait a longer period of time, interval, for the geyser to reload and erupt again. The code for doing something like this is on overhead number 5. The data set is called Old Faith. It's a built-in data set into the ALR3 package. I show the code there on the left for doing the plot command, and I show a command, the LM function, for producing a summary line, and then the AB line command produces and puts the summary line on the display. You'll notice on the scatterplot command it is always of the form Y response variable tilde as a function of the X variable duration. And here you can see the graph that's produced by these commands. The simple linear regression model is a mathematical representation about how data gets constructed. Like, for example, on this graph of the duration variable and the interval variable. How do these data points get generated in some mathematical system? Well, one thing you might think is reasonable, since this appears to be an upward trending kind of relationship, something that might be reasonable is to think it works like this, the simple linear regression model. What this says is that the Y variable, the variable here called interval, gets produced by this kind of mathematical structure. And you'll notice what we have is beta naught, which controls the intercept of a straight line, and beta 1, which is the slope of a straight line, related to the X variable, the time that it took the Old Faithful geyser to erupt, or how long the last eruption was. And plus a little piece of random error. And this signifies how a data value Y gets generated from a particular value of X. On the next overhead you can sort of see the structure. So if we know the last eruption took a value of 3, for example, what we do to generate a waiting time is plug 3 into this linear equation, beta naught plus beta 1 times X, where X equals 3, and it would put us about here on the straight line mean function. And that's what's being represented here by the beta naught plus the beta 1 times the X. These first two pieces are defining the mean function. If you tell me a value of the predictor variable X, we can come up with an estimated average for what the response will be. And then noticing that on real data and real scatter plots like this, the Y variables don't exactly fall on a straight line. Some of the waiting time intervals are above what we would expect from the mean function, and some of them are below, and that randomness that we see in the scatter plot gets modeled by these random error terms E sub I, where the subscript i's just signify the ith observation. And so this is often a quite reasonable mathematical statistical representation for how data could theoretically be generated. Now, this kind of data generation system isn't going to be always exactly true, but it can be very useful if it's approximately true, and we can get some really great results even with systems that are only really approximately generated like this. So there's a famous old saying that says, all models are wrong, but some are useful. And this is a case where data is often similar enough to this kind of structure that this simplification is really quite useful. So as I've mentioned, the beta naught parameter controls the y-intercept. The beta 1 parameter controls the slope of the relationship between y and x, and the random error parts are controlled by this EI. And as I say in the third bullet, the variation in those random errors is controlled by a parameter sigma. And sigma controls how much variation there is in data values around the straight line mean function. And so on this particular overhead number 7, you can see that the tilt of the relationship is being controlled by beta 1. That controls the underlying rate of change between the data values. Beta naught controls the upward shift where the y values will be located. And then there is a parameter sigma that controls the spread around that mean function. And here on overhead 8, you can see the three pieces. This line that's going through here is the mean function, and then these little bell-shaped distributions are meant to communicate the variation in the random errors, the sigma of how much variation y values will have above or below the particular place on the mean function. And so therefore, these three components, the intercept, the slope, and the sigma standard deviation of the randomness, basically control how observed data comes to us. This is a description of the data creation mechanism that we see in a scatter plot when we start analyzing data, and we look at it and we say, well, what kind of data generating system could have produced this? And we might think that something like this simple linear regression model might be a reasonable thing to presume. And we'll proceed with analyzing in that fashion. Here are the model assumptions. This is a very crucial part of the course to understand what this data creation system assumptions are and what simplifications we're making. The first bullet says that our randomness components are assumed to be random and on average take on the value of 0. So on average, y values are possibly above the mean function or below the mean function. A random error value of 0 would mean that the y value is being placed right on, exactly on the mean function, right exactly on, say, this line. That's what it would mean for a random error component to be 0. What we're presuming here is that on average they're 0, and sometimes they might be above 0, which would put a y value above the mean function. Sometimes you might have a random error that would be negative, and that would put you below the generating mean function. That's what this first assumption is. Remember that the capital E means expected value of, so on average our errors are 0, even though any individual error might not actually be 0. On average they're 0. The next bullet says that we are going to assume that these random error pieces have the same standard deviation for all the data values, the first data value we have up to the nth one. The third bullet says that we're going to assume that our observations are all independent, that the random errors are independent from each other. Whatever one data observation random error would be does not tell us anything about another observation's random error. The fourth bullet says that we're going to tell you about an assumption that is frequently made, that the error distribution, that these error values have a bell-shaped random normal distribution. This is often assumed, but it is not crucial, and I sometimes don't really include this as one of the assumptions, but in many places this is a standard assumption, even though for me I don't typically include it. It's not really necessary for everything we do. It does come into play at times, and I'll tell you when that occurs. The graph that I have drawn here on this overhead number 8 is illustrating that the random error components have a bell-shaped distribution. And what I'm saying is that this is not entirely crucial that this be exactly bell-shaped. It could be just mound-shaped or flat or something else. But it is typically an assumption in some books, even though I'm not going to stress this fourth one. What we're talking about next is, well, if we observe a scatter plot of data and we would like to estimate and think about the simple linear regression model being a reasonable thing to say about these data, we might want to use our observed data and estimate and come up with guesses for what the data generating mechanism would be like. What do we think it could be that would have generated the data we see? And that means coming up with estimates. And the kind of estimates we make are called least squares estimates. And to understand this, first of all, we need to understand the idea of a residual, and that's a random error with a hat on it. And it just consists of the observed y value for a particular case minus what we would estimate it to be from a summary estimating line. And on the next overhead, I sort of illustrate that idea. Right here, this would be an observed y value of about 3.2, and the data estimated y value for this particular value of x looks like it's about 2.3. And so the residual is represented by these vertical distances. These vertical distances represent distance between a y value and the estimated summary line that goes through those y values the best. And so least squares estimates just mean put a straight line through our y and x values such that these little squared distances are as small as possible. We minimize the residual sum of squares. And so what's going on here is, notice inside the parentheses, that's just the definition of a residual. That's just one of these little distances, either positive ones or negative ones if the data value y is below the line. That's what's inside this parentheses. And then we square that residual. And then what this summation means is we're going to add up every one of these squared residuals from the first data value to the nth one. And what we're trying to do is make this sum of squared error distances as small as we can, as small as possible. And visually that just means put a line through these y data values that goes through the values the best they can and makes these distances as small as we can make them. That's what least squares estimates mean. Find the slope, find the intercept, so that the line that you're estimating goes through these points well. Here are the formulas that R uses to calculate these estimates. Here's an expression for the best slope that will produce a line that goes through the points. Next, we come up with a formula for the best intercept that will take us through those points. And the third bullet tells us, well, If we want to estimate what the variation is above and below the data generating mean function sigma, if we want to come up with an estimate of sigma, the random error variation, here's an estimate of that as well. And the fourth bullet tells you the computing expressions for these things. So SXY just measures the sum of these little differences between the y values and their average and the x values and their average, and that forms the numerator of the slope, and the denominator of the slope is called SXX, and that is just the sum of the squared differences between the predictor values and their average. So this is a total predictor variation in the denominator against a kind of scaled x against y variation in the numerator. And together those things produce an estimate of tilt or slope in the line that's the best it can be. The formula for the estimated intercept is given here, and then we use the residual sum of squares to come up with an estimate of variation around the true mean function. You don't need to really remember these formulas, but I do want to show them to you so that you know what R is computing when you get output from an R-based analysis. Now I'm going to talk about some properties of these estimates and how you should expect them to work. Some of the properties are to understand what's the expected value of an estimate. If we use this particular kind of estimating formula over and over again on samples from the same data generating mechanism, like this formula right here for the slope, how does this slope formula work from one sample to another from the same data generating mechanism? There are some patterns. We're going to learn those patterns. So one of the important things is what is going to happen on average, and another important thing is to understand how much variation is there going to be in an estimate like this from one sample to another. How much variation is there going to be? So typical value and typical amount of spread are important issues. The third bullet says that we're going to be able to come up with expressions that are going to be estimates of the variance, and an estimated standard deviation of one of these beta hat estimates is called a standard error, and we are going to find standard errors by just replacing the real data generating mechanism standard deviation sigma by a data-based estimate of that variation sigma hat, remembering that sigma hat comes from our data values like the third bullet on the previous overhead 12. And so let's talk about the slope estimate to start with. And what this slide tells us is that on average, when you make slope estimates from observed data using the formula I just showed you, SXY over SXX, what this result says is that on average, data estimates take on the real value of the data generating mechanism, the real slope, beta 1. That's a really important feature. It means that on average, our data estimates are around the right thing. Sometimes a data estimated slope will be a little bit too big, or maybe a little bit too small in one sample or another, but across samples, on average, we get the right thing. That's what this overhead says. The next slide, slide 15, tells us what the variation will be. And you will notice that this formula is always going to be a positive value. Sigma just represents how much variation the data generating mechanism has in the little e error terms, and the smallest that could ever be is 0. And the denominator, remember, is the square root of SXX, where SXX is just measuring the variation in the predictor values. And so the three bullets sort of tell you what you should be expecting to happen here. When there's more randomness and noise in the data generating mechanism, in other words, sigma being bigger, there's more dispersion in the y values around the generating system, and that means you're going to have more uncertainty and more standard deviation of an estimate. Your estimate is going to be more variable. And that makes sense, I think. More data randomness in the data points should mean more uncertainty and more variation in the estimating process. You'll notice that another thing that matters is down in the denominator, the value of SXX. When SXX gets bigger, the variation in the estimate gets smaller, or in other words, you get a better estimate, less variable estimate. Well, when does SXX get bigger? Well, remember, it gets bigger because it is the spread in the predictor values around the predictor average. And when can this expression get bigger? Well, it can get bigger when you add more values together. In other words, when there's more data values, this sum of little positive contributions, it gets bigger. So more data will make this bigger, and so therefore more data will reduce the variation in the estimate. That makes sense, I think. More information should produce less variable estimates. But you'll notice there's a spread issue, and that as the predictor values would spread out away from their average more and more and more, you get a more precise estimate of the tilt or the slope. I think that also makes sense as well. Same kind of properties are true for the intercept. On average, the intercept estimate tends to be whatever the truth is back in the data generating system. That's, again, a very desirable feature. And for the standard deviation, you will notice that uncertainty or standard deviation goes up when the error generating part of the noise and the randomness in the system, sigma, goes up. You will notice that this standard deviation goes down when there's more data, n, and there's more data n going into the SXX, and that makes that smaller as well. So more data will make the standard deviation smaller. More spread in the predictors makes it smaller. But you'll notice that there's a component here of x bar squared. And in other words, if your predictor values are drifting away from 0, the standard deviation or the uncertainty in your intercept gets bigger and bigger, and you have more uncertainty in your estimate. And I think that makes sense because if your data is drifting away from x equals 0, this beta naught is really a question about what the response behavior is like when x is 0. And if your data and your information is drifting away from 0, you have less reliability and less ability to say about what's going to happen around 0. And so I think it does make sense that your estimate will get, your standard deviation of this estimate will get bigger, and you'll be less certain about what it's doing as you drift away from 0. The two slope and intercept estimates on this overhead shows that they are negatively correlated with each other. The covariance between the two estimates has a negative number, and that just signifies that when slope goes up, the intercept tends to go down, and when the slope goes down, the intercept goes up. Just take your finger or your arm and change the tilt of your finger, and you'll notice the intercept part goes up and the slope part goes down, and vice versa. That's what that's signifying. Here's how you do things in R. We would have a data set called Old Faith, and we're going to estimate the simple linear regression model in this third command using the LM function for a linear model. And we're going to use the response variable interval, explain it by duration, use the data frame Old Faith, and then from the data model object called Old Faithful mod, that is a model object, I have printed a summary of that object right here, at least the coefficients of it. and you'll see the estimated intercept is 33.987. Under the estimate column, that would signify beta naught hat. The estimated slope of the best summary line for these data is beta 1 hat, and that's 0.1768. It's right here under the duration row. 0.1768 is going to be our estimated slope. The next column in the output table tells us the standard error estimates. Those are the things that I showed you the formulas of right back here. The estimated standard deviation for the intercept would be found by putting an estimated sigma hat into this formula, and it would give you this value right here, 1.181. That would be the estimated variation of the intercept, and the estimated variation of the slope is about 0.0053, and that tells you basically how much will a beta 1 hat slope estimate change from this sample to the next sample of the same sample size. You should expect the slope to differ by about 0.005 units. And so I would expect an estimate like this one to change from sample to sample by this standard error amount. In terms of our data set, what do these numbers mean? Well, an intercept means what do you think the response will be if the predictor value was 0? Well, the predictor value 0 means that the last eruption took 0 seconds. How long should we expect to wait for such a previous eruption? And what this says is we should expect to wait about 34 minutes. No matter what the eruption was, for 0 seconds of previous eruption, you should expect to be waiting about 34 minutes. The slope tells you, this 0.177, that basically tells you how many additional seconds, how many additional minutes you're going to have to wait for an eruption that took an additional minute of duration. So for 1 additional minute of duration, you should expect to wait about 0.177 additional minutes. And so that tells you that you're going to have to wait longer if the previous eruption lasted longer. And we know basically how much another second of eruption will cost you. Another second will cost you part of a minute. Next part of what I need to tell you about is this decomposition of variation. And what I'm saying here on the left-hand side of this equation is that the distance between an observed y value and an average value of the response can be broken into 2 pieces. The first piece you'll recognize is just the residual. It's how far the y response observation is from what we predict from the least squares summary line, and then a portion that measures the distance between the summary line and the overall average. If you look at this right-hand side, you'll see we've just added and subtracted y hat to maintain the equality. But this adding and subtracting, adding in a 0, basically produces a decomposition that is kind of helpful. And what it says is that you can break up the distance between a y value and its average into 2 parts. The part between the y value and the line, and the line and the overall average. We call this part between the y value and the line the residual part, and we'll make residual sum of squares variation from this component. And the second component is going to be called the variation from the regression or from the model, and we'll be calling it sum of squares regression. And this partitioning is often summarized in what is called an ANOVA table. And all ANOVA tables basically have this same form. We have a line for the regression model portion, and we have a line or a row for the residual portion, and then it makes a total altogether. And ANOVA tables are always formed by a first column being source, a second column called degrees of freedom, which tells you basically the dimension or the size of this particular component in terms of its dimensionality. And then we have an SS, or sum of squares component, of how big the variation is. And then we always have a mean square column denoted MS, and that is always the respective sum of squares divided by the degrees of freedom. So for the mean square for residual, it's just the residual sum of squares divided by n minus 2. And that forms a mean square. And then finally there's going to be a test statistic involved, F, which is going to be the division of the two mean squares. The mean square for regression divided by the mean square for residual. And we'll be talking about this one in a moment. Notice that when you take the residual sums of squares and you divide it by the degrees of freedom, it is an estimate of the error variation in the data creation system. And that forms our estimated sigma. You can get an idea about these components from R by using the ANOVA command. So if you have an estimated least squares model like OF mod or Old Faithful mod like we generated earlier in the overheads, you can type the ANOVA command and you'll get this decomposition. The regression part from the model with 1 degree of freedom, variation of 39,358 between the summary line and the overall average, and then you'll notice the row for residuals has much less variation around data values around the line compared to how the line differs from the overall average. Then we have a mean square and an F and a p-value section, which we'll also talk about later in this presentation. Part of doing this decomposition is to get a measure of strength of relationship called R squared. And that's just the division of the residual sum of the regression sum of squares divided by the total sum of squares SYY. And the nice thing about this is it's an interpretation. It's the fraction of variation in the response that can be explained by the predictor. So in terms of our Old Faithful geyser, you'll look down in the bottom of this model output and you'll see, created from the summary command, you'll see that we have an R squared down here of 0.8029. This will be the value of R squared that we use. You will notice that right above it is our estimate sigma hat that comes from the residual sums of squares divided by the degrees of freedom, all square root. And so sigma hat would be about 6 here in this case. On the next overhead, we'll go through the interpretation of R squared, 0.8029. What does that mean? Well, it's the percentage of variation in waiting times that can be explained by knowing how long the last eruption was. So in other words, in the second bullet, 80.29% of the variation in waiting times can be explained by how long the last eruption was. So in other words, about 80% of the variation, or 80% of what's going on in that relationship is explained by the waiting times. So it's not a perfect explanation. Knowing how long the last eruption was is not a perfect predictor, but it is quite good. Higher values of R squared mean a stronger relationship and a better performing predictor. We're going to move on now to parameter inference, and that's going to be in the next part of our presentations. Let us know if you have questions about this one.